And there we go. All right, so the YouTube stream should start in about, give it 10 seconds or so. All right, it's actually longer than that. All right, so YouTube is up. And let me just check the voice on the other side. Give it 10 seconds or so. That's working. All right. So what we'll do today is we are continuing with the topic of relations, unless people have questions about the exam. So let me just give you guys another reminder, okay, to make sure that you find the form, to let me know what time slots you cannot make it, for the first exam on next Tuesday. So
Oh, so that form is for us what we cannot make, not what we want.
that is for the time slots that you cannot make it. That is correct. It's an exclusion list, not an inclusion list. All right. So because I do it this way because people who basically say I can do any time slot, they don't have to turn in anything. Instead of checking every single box, or have one box that says I can make it to all the time slots. People who just do not turn in anything, I would just consider that as okay, the entire day is okay with me. Just arrange me to any time slot that is convenient. So that's why I use an exclusion list instead of an inclusion list. Yeah, go ahead.
Never mind, you just answered it for me.
Oh, okay. All right. Very good. The Design Hub people, some of the Design Hub people also found a denoiser that works for Windows as well as Mac OS 10. So if you live in a household and things can get a little bit noisy, you can use a headphone, okay, to help isolate noise when you're trying to hear something, but your mic will still pick up everything from the background. So if that is an issue, I can look it up if anyone is interested, about the software that you can install in Windows and also Mac OS 10 to help minimize the noise that you're transmitting out. That the mic is still picking it up, but the software is doing the denoising. So if you're interested, let me know, and I'll go ahead and find that particular program that works in Windows and Mac OS 10. All right, so back to relations. Okay, this is it's an interesting module. Okay, because okay, open up. There we go. All right. So we talked about relations already. We have already started to talk about it, and we know that a relation is a subset of the Cartesian product of the set that the relation is defined over. So what we'll do today is we are jumping into the special properties. So the special properties, I think we might have started to talk about the reflexive property already. But I can just kind of go over this really kind of quickly again. A relation R over a set X is said to be reflexive if and only if the following is true. So we need this particular statement to be true, which basically says if you pick out any element from X, the element E should relate to itself in the relation R. Okay. Now, let me just kind of go back and give you some examples because I think working out examples typically help people understand the concepts because now we can look at different scenarios. So let me do this. And today is 0924. I'm just working out the markdown file on the side. All right, so now we can look at examples of reflexive relations. Okay. All right, so the first thing we need to do whenever we want to define a relation, we have to first identify what set is this relation working over, okay? So we have to define a particular set first. So in this case, I'll just define that set and call that X, okay? And we'll say, it has elements A, B, and C in this particular set, okay? So now we want to look into individual relations that we can define over this particular set X, and we want to ask, is it reflexive? Okay, so we'll first start with an empty set. Okay, so if R is empty, okay, so we want to know whether R is reflexive or not. Okay, so we will call this R to be a relation defined over X, but it is empty. So is it reflexive or not? It is not reflexive. It's not reflexive because if I pick out any element from X, let's just say A, okay, and we look into the relation R, AA as a two-tuple is not found in R, which means A does not relate to itself. But in order for a relation to be reflexive, we need every element to be relating to itself. So this particular R is not reflexive. Let's look at another example. Okay, so this time we have R having AA in it. Okay, well, this one is also not reflexive. Reflexive, and I need a close $ right here. There we go. So this R is also not reflexive because even though for one particular element A in X, it relates to itself through this particular relation, but when you look at another element, let's say B or C, they do not relate to themselves in this particular R. We need every single element to relate to itself. So as a result, this particular example of a relation R is also not reflexive. So that brings us to the third example, where we have AA, BB, and CC. All right. So this one has got to be reflexive, right? Because, if you look into this particular R and you ask, does A relate to itself? The answer is yes. Does B relate to itself? Yes. Does C relate to itself? Yes. So it is definitely meeting all the requirements of a relation being reflexive. So we'll say this is reflexive, okay? So now I'm just doing a very lazy thing, and I'm just adding one more element here. Okay, we are adding, let's say, AB over here. So in the fourth example, this particular relation R is a reflexive. Okay, so that's the question. So now we have to go back to the definition of being reflexive, because that is super important now. Okay. Now this says for every element E in X, it has to relate to itself. This is the only requirement of being reflexive. So when we look at the fourth example over here, and we ask the same question, does A relate to itself? Yep, AA is here. Does B relate to itself? Yes, BB is over here. And then does C relate to itself? The answer is also yes. Then you go like, okay, that seems to meet all the requirements, but what about this extra thing that A relates to B? It has nothing to do with whether a relation is reflexive or not. In other words, you can have extra stuff in a relation, but as long as every element relates to itself, the relation itself is still considered reflexive. So this is important. Do we have any questions about any one of these four examples? Two of which are not reflexive and two are reflexive. So we good over here? All right, cool. So how is my voice working out here with the noise canceling plugin?
Hello?
Hello? I can hear you, Catherine. Oh, okay. All right. Okay, so back to this class. I got two questions for you guys. One is, do we have any questions about the four examples? And two, is my voice working out okay? All right, so we got Catherine typing here. All right.
Yeah, yeah, your voice is doing all right.
Okay, thank you, Aaron. All right. All right, that's not a problem. All right, so let's move on to the next one. Okay, the next one is symmetric. Now, when you look at the definitions between reflexive and symmetric, symmetric is a little bit trickier because it has this if and only if or equivalence, okay? So now we have to look into this and go like, okay, we got to be careful because unlike reflexive, okay, so we'll say examples. Okay, you guys cannot see what I'm typing just yet. Let me type this first, and then we'll switch to the whiteboard. This is symmetry. All right. Oh, okay. It's not a problem, Catherine. Don't worry about it. All right. Right. So when you watch Discord on the phone, it has limitations. No problem. Don't worry about it. We're good. So let's talk about symmetry. So let's look at the definition first. Okay. So for symmetry, we say for every way to choose E and F being elements of X. Okay. So does that mean E and F have to be different? Nope. Okay. It doesn't mean that E and F have to be different. They can be the same. So you can kind of look at this as a double loop. The outer loop is basically saying for every single way to pick E in the set X, and then you have a nested loop that says for every single way to pick F in the same set. Okay, and those two loops do not exclude an element being picked again. So the same value of the set X can be chosen as E and F. Okay, so that is the first part that is important. But what is the statement that we want to say about EF? So the statement has an if and only if. So it reads as EF is in R if and only if FE is also in R. Okay. So this is really important because all it is saying is if it is here, if one is here, the other one had better be here. Okay. If one is not here, then the other one had better be also not here. Okay. That is symmetry. So if you guys can kind of open up your own browser to stay on this particular definition, then I'll switch over to the whiteboard because now I'll give you some examples. So the example I'm going to give you is the same X. Okay, so just to be super lazy, okay, I'll put X over here. And now we will define R. And then we'll say, is that R symmetric or not? So just like before, we look at the empty relation first. The empty relation is not reflexive because none of the element is relating to itself, and we need all of them to relate to itself in order to be reflexive. But when we talk about symmetry, then we just want to make sure that if AB is not here, then BA should not be here either. Okay, if BC is not here, then CB should not be here either. So the empty relation, very interestingly, is actually symmetric. Okay, is symmetric. Okay, so that is rather kind of interesting. So we copy and paste this, and this time we introduce one particular element in it, which is just AA. Okay, A relates to itself. So now we ask, is this particular relation symmetric over X? X being the set of A, B, and C. The answer is yes, this is also symmetric because AA is, because now we pick A as E and A as F, okay, in the notation. So now we say, okay, we find EF in R, but we also find FE in R because EF and FE are really kind of the same thing. But the if and only if still works out. Okay, so it is still symmetric. So now we ask, what about this one over here? Okay, so we have AB. So AA and AB are the elements. This one is not symmetric. This one is not symmetric because AA is fine. Okay, that is not our problem. But AB is a problem because AB is in R, but BA is not in R. So that makes the if and only if false. Because if and only if says if the left-hand side is true, then the right-hand side should be true too. And this time we do not have that because BA is not here. So if we want to add one more element to make it symmetric, then we just add BA here. Now it is symmetric again. So do we have any questions about symmetry? What makes a relation symmetric? Okay, no questions? Not even the first one? Yeah, why the empty relation is symmetric?
Is that symmetric because there's nothing to reflect against?
It is symmetric because for every way to choose two elements, none is in the set, right? So if you go back to the definition, of symmetry, so that means no matter what you choose as E and no matter what you choose as F, EF is in R is guaranteed to be false. FE in R is also guaranteed to be false. So now we have false if and only if false. That makes the if and only if true. Does that kind of make sense? I know it sounds confusing, but does that make sense?
Yeah.
Okay. Yeah, so the idea of the empty relation being symmetric is because both sides of the if and only if are guaranteed false because R is empty, so there's nothing in it.
Yeah, that makes sense.
Okay, all right, cool. And any other questions about symmetry before we move on? Okay, no more questions here. All right, so let's move on to transitive. So we are moving on to this one. So transitive is also interesting because you need to pick 3 elements from X in order to express, whether that particular way of choosing the 3 elements is transitive or not. So this means, okay, the first part here basically means, um, pick E, F, and G, each one as an element of X. But they can be the same, okay? You can pick the same element as E and as F and also as G, but you can also pick entirely different elements as well. But no matter how you choose E, F, and G, we want this expression here to be true. So let's take a closer look at this particular expression. It says EF in R and FG in R implies EG in R. So this one is not if and only if, it is just an implication, which means the only time the implication is false is when you have the conjunction, this entire conjunction being true, but the membership being false. Okay, that's the only time you can make an implication false. Okay, so go ahead and try to remember this one, and then I'll switch over to the whiteboard to give you guys some examples. There we go. And now we are moving on to examples of transitive relations. All right, so we'll use exactly the same set for our X. Okay, so we are now defining relation R over X. And just like before, we want to look at the empty set and ask, is the empty set transitive or not? Okay, that's our first question. So is it or is it not transitive? So I want you guys to think about this, because I worked out the other 2, in relation to the relation itself being empty. So I want you guys to kind of work this out. Okay. In other words, I want you guys to work out this particular implication. Can you find an instance of picking E, F, and G in set X so that EF in R and FG in R is true, but EG in R is false? So that really is what the question is asking. I'll give you guys like 10 seconds or so to think
Would
about
that
it.
make only the very last one, the AA, BB, CC, AB, transitive, and all the other ones not?
Well, we'll work on this one first. We'll just work on the empty relation first. We'll get back to the other one, okay? We'll get back to all the other ways of defining R, but right now, we are only focusing on R being an empty set. So R being an empty set, does it mean that it is automatically transitive or is it automatically not transitive? That is the question. All right, I'm not seeing any text channel content.
I'm gonna go with it's not transitive.
All right. Anyone else? All right. So the answer is it is transitive. Why is it transitive? An empty relation is by default transitive. That's because R is empty, right? R is an empty set in this particular example. So that means no matter how you choose E, F, and G, E, F as a two tuple in R is guaranteed false because there's nothing in R. Well, this is a conjunction, so we don't even have to bother to look at FG, because if EF in R is false, then the conjunction has to be false. But when you have the left-hand side, or the precedent of an implication being false, then the implication itself is true already. So I don't even have to bother to look at whether EG is in R or not, because I know EF in R is guaranteed false when R is empty. Does that make sense?
Yep.
Okay, excellent. And do we have any questions before we move on? All right. So now we move on to antisymmetric, which is also reliant on implication. But the way it relies on implication is a little bit different. Oh, wait, I cannot do that yet. Okay, because I want to give you guys more examples. Just having one is not enough. Okay, so let's pick out this one. Okay, let me finish this sentence first. Is indeed transitive. There we go. So now we look at what Aaron wanted to look at a little bit earlier, whether this one is transitive or not. Okay, so I will let you guys think about it. Okay, is this particular R, the second example, is it transitive or not?
I would go with no, since C is not in any of the relations.
Okay, so C is not in any one of the C. Okay, there's nothing. There are no two tuples in R that mentions C at all. Okay, that is correct. Okay, but does that mean R is not transitive? Okay, so what we want to know, okay, so what we want to see is what if we pick C as one of the E, F, and G, right? Okay, so let's just say that, in the definition of being transitive, we pick out F to be C. Okay, all right. So that means EF in R is guaranteed false. So we get back into the same logic, where we basically say, hey, one of these two conjunctions is guaranteed false anyway. So the conjunction itself is false. When the conjunction is false, then the implication is guaranteed true. So that's why, in the second example, R is actually transitive.
Tack in in that function, or not function, but the rule that you gave us for each A or E, F, G. Does the order matter?
Does the order matter? What do you mean by order?
Of E, F, and G.
Yeah, but I'm not sure what you mean by order, because they are picked out from a set.
Yeah.
Right?
So like in our example of X equals the set of A, B, C. Does A, B, and C have to be in order A, B, C, or can it be in any order?
In any order. Order is significant.
Okay.
Okay, so in order for any one of you to convince me that R is not transitive, then you have to use an example. Okay, you have to basically pick an example where you say E equals to A, F equals to B, G equals to C, or something along that line, such that whatever expression is in here is false. Okay, so you have to give me a case where this is false, then I'll be convinced that this particular R that we are talking about, the second R, is not transitive. So that would be the challenge. Okay, if you think this R is not transitive, then you have to prove that there's at least one way to choose element E, F, and G, so that the expression inside the quantifier is false, at least for that particular way of choosing E, F, and G. Does anyone want to try? I don't mean to ask it as a challenge. I mean to ask it as, okay, we can try out combinations of choosing for variables e, f, and g, and I can show you why no matter how you choose it, the expression is always going to be true. The implication is always going to be true. So I can, if you want to get a better understanding of implication, now would be a good chance. Alrighty.
Are we able to use just all A's? So AA.
Okay, let's pick that. Yep, we can certainly do that. So now we want to look at one particular example where E is A, F is A, and so is G, right? So that's what we want to choose as an example, right? Yes?
Yep.
Okay. So in this particular case, then we are evaluating something like this, okay? We are evaluating AA and AA implies AA. Actually, let me refine this a little bit, because we have to use in R. Okay, everything is in R, so we can use the other notation where it says ARA, but I think it's better to do it this way so that it is clear that we are using set notations or set concepts. So now we want to look at this particular implication and ask, is this implication true or not? So AA is in R. Yep. AA is in R. Yep. So we have yes and true and true, which is true. Implies AA is in R, which is also true. So true implies true is true. So if you choose E, F, and G all being A, then the implication is indeed true. Does that make sense?
Yeah.
Okay. Any other examples that you guys want me to kind of go through and explain? All right. If there are no other examples, let's choose. Yeah, go ahead.
Excuse me, Professor.
Mm-hmm.
I have a quick question. I didn't understand why the last exam of symmetry is not symmetry. Why?
Oh, that's because
the last exam of symmetry.
That's because I copied and pasted without changing the pasted one.
Oh, that's right.
that is my mistake.
Because I checked it out, several times. I saw it is symmetric, but why?
Yeah, that was my mistake.
It's okay.
Because I said, let's add one more element to make it symmetric, and then I forgot to change the text.
At least I noticed I'm right.
Yes. And
thank you.
This is also a very good example of why copy, paste, and modify is not a very good coding technique, right? Because you can copy and paste and then just completely forget to change what you're supposed to change.
Sometimes, it messes up. I know.
Thank you. Sure, you're welcome. And I'm glad that you can make it to the Discord side too, because this is a whole lot more interactive in real time.
Oh yeah.
Yep. Okay, so Omar has a point, and he says, so it also works for AB and BA because the right side of the implication would be AA. That is correct. Okay, so let's work with what Omar said in Discord. So this time we are picking A and then B and then A. Okay, so that's basically the configuration that Omar is mentioning, is to make E equal to A, F equals to B, and then G equals to A again. So now we have AB in R and BA in R, and we have implication of AA in R. And that turns out to be true as well, because AB is right here, BA is right here, and then AA is right here. That is all correct. So very good. Okay, so this particular R is indeed transitive, because we cannot find a single way of choosing elements for E, F, and G so that the implication itself is false. All right, so let's go ahead and work on some more examples, because I think the more examples we can kind of go through here, the better we can understand what it means when we say a set is, a relation is transitive. Okay, so in this case, let's have AA, let's have AB, and then we have AC, and that's it. Okay, this is the relation that we are talking about. So the question is this transitive or not? So instead of thinking about transitivity like in algebra, I would encourage you to look at it using the quantifier. Basically, you're looking for a way to choose elements, for variables E, F, and G, so that the implication is false. Okay. So Omar says, I think not, or I think no. Okay, Aaron, go ahead.
I also don't think it's not.
It is not transitive? Okay.
Because if you'd need one more set, would you not?
Okay, so I'll put it this way. Okay, so don't copy it, because there's a question mark of the not, which means we are asking, is it not transitive? So if you think it is not transitive, then you have to give me a way of choosing E, F, and G so that the implication is false. So go.
I think it is. I think it is transitive because the first statement is false.
The first statement
yes,
is false.
in a condition, for example, we don't have A, B in R and then B and C on R.
Okay, so Yalas is correct. There's no way to. Okay, let me go back to the definition. So Yalas is correct. Did I pronounce your name right? Yalas.
Yes, that's right. Okay. Perfect. Thank you.
So Yalas is correct, because in transitive, we need both. Okay, there's a conjunction here, right? So we need to have we need to be able to find an element F, quote unquote, as a bridge. Okay, so which means we have to find F as the second item of one two tuple, and then we have to find F as the first element of another two tuple. In the example that I have here, you cannot. A does not do it, right? Because A is always the first one in a two tuple. B is always the second one in a two tuple, and C is also always the second in a two tuple. So we cannot find a single element, a single value in X that is the second one in one two tuple and the first in another two tuple, which basically means the conjunction here is guaranteed false. Let me go back to the correct one. That means this conjunction is guaranteed false, because we cannot find what I would call a bridge element. Now don't quote me, okay? There's no actual technical term that I know of that F is called a bridge element, but I call it a bridge element because it is bridging between E and G in a transitive setup. So in this particular one, we don't have a bridge, which basically means the conjunction itself is always false. So if the conjunction, which is the precedent of an implication, is always false, then the implication is always true. So that means the relation itself is indeed transitive. So I'll go back here and edit it so that it is transitive. Okay, so it looks kind of awkward, right? Because intuition tells us that, nah, this one cannot be transitive, but it turns out to be actually transitive. So let's go ahead and take a look at something that is not transitive. Okay, so we'll have, this one is going to be fun. You guys will like it. So we have AB and BA, and that's it. Okay, so I'm not going to even bother to ask you whether it's transitive or not, because I said already that this is not transitive, right? So you look at this and go like, but this looks really nice. I mean, it looks kind of symmetric, and things are very even, okay? But it is not transitive. And then someone would probably look at a previous example, right? The second example of transitive relations, which is this one over here, and ask, but this one is transitive. How come this one is not? Well, it's exactly the second case here, okay? So when you look at this particular expression, it is false, okay? So let me just write it down here so you can see what I mean over here. So if I choose E to be A, and I choose F to be B, and I choose G to be A again, okay, then the implication is false, okay, because now we end up with AB in R, which is true, okay, and BA in R, which is also true, but then we have an implication of AA, okay, which is false, or AA in R. So let me highlight here which portion is true and which portion is false. This portion is true because we have AB here. This portion is also true because we have BA over here. So that means the conjunction as a whole is true because we have true and true. And then we have the implication here. But when you look at the consequent of the implication, which is the right-hand side of the implication, AA in R is not true because AA is definitely not in this particular R. So that means we have true implies false. That makes the implication itself false. Now, since I can find one example of choosing values for E, F, and G such that the expression is false, that means the entire quantified statement is also false because we need this part to be true no matter how we choose values for E, F, and G. All right, so are we okay with this particular example? You know, why this R is not transitive. This is a kind of tricky one. You know, in previous semesters, in exam 2, a lot of people got this type of concept wrong. A lot of people do not understand why this particular R here is transitive and then this one is not.
Excuse me, Professor.
Yeah, go ahead.
I thought even this third exam, if we have the third exam of transitive, would not be transitive. The third one.
The third one.
The third exam, yes.
This
because
one?
we have the third one in transitive.
You mean this one, right?
I mean the second one.
This one?
The second, yes.
This one is transitive.
Because I think it would not transitive because we have BA and AB, but we don't have BB.
Oh, you're right. Okay, very good. Thank you, Yales.
Sure.
You are right. This is actually not transitive. I forgot about that one.
It's okay.
Okay, so let me explain why it is not transitive. The exact way of choosing what is in E, F, and G that will make it not transitive. This will make it not transitive.
It was a little bit tricky because we didn't notice BA and AB. We just started from left to right. That is why.
Yep. So we have BA, and then we have AB, but then BB is not in the R. So we have BB. Oops. BB. Whoop.
So would it be transitive for everything but the case of BB then?
Huh? Say one more time.
So in that case, would it be transitive in every case but the case of BB?
Okay, but you only have to find one way to choose E, F, and G such that the expression is not true for the relation itself not to be transitive.
Okay.
Because that's the whole idea of the for all. Because for all basically says, you know, for every single way of choosing something for that particular variable. So if there's one way of choosing a combination of the variables E, F, and G so that the expression is false, that means the entire quantified expression is false. Because in this case, we're using a universal quantifier. Is that okay?
Professor, I'm still a little confused about how the AB-AC relation is transitive then. Would you be able to do it the same way you showed for the other examples?
Okay, so all right, so if you want the solid proof, it's going to be extremely tedious because you know we basically have to look at every single way of choosing the three elements. Okay, I can show you what it's going to look like in a spreadsheet. So give me a second here to fire up a spreadsheet. I'm not. Well, I don't know. I'm just thinking about whether I should use my local spreadsheet or whether I should use a Google Sheet. I think I can always use a local spreadsheet and then later on translate that or upload it to Google Drive. So we'll cancel that, and there we go. All right. So if you want a solid proof, like a positive proof that ABAC, is transitive, then what we need to do is to say, okay, let's consider every single way of choosing E, F, and G. So E can be A, right? So we'll put A, 4, 5, 6, 7, 8, 9. And then same with B, right? 1, 2, 3, 4, 5, 6, 7, 8. And then C is the same way. 1, 2, 3, 4, 5, 6, 7, 8. Okay, is it 8? Or is it? No, that's 8, 9. There we go. Okay, because we should have 27 items, which means we should end up with 28. So I'm miscounting something here.
I think you only put 8 Bs.
Oh, then okay. So we'll go ahead and insert one more row for the Bs. Okay. Oops. B, not B. There we go. B. There we go. Okay. Now, when E is A, F can be A, B, or C, right? And this time it's easier because now I can copy and paste. So when E is B, then F can also be A, B, or C. And when E is C, F can also be A, B, or C. Now, when E, F are both A's, then G can also be A, B, or C. When E is A, F is B, G can also be A, B, or C. So obviously, this is just going to be another copy and paste. There's a programmatic way to generate this table using mod, and it's basically a base conversion thing. Okay, but I'm not going to go that route because it just adds complexity unnecessarily. So this way I can kind of explain it as we get onto this. Okay, so for every single row, okay, now we want to evaluate the expression. Okay, so now we need to evaluate the expression and see whether it is true or not. Okay, so now we are asking when E is A, F is A, and G is A, and R is only having AB and AC in it, is the expression true or not? Okay, so I'll work out a few examples, but you guys will get the idea, right? So in this case, this is just, I'm just typing it. There's no actual equation here. So I'll say AA is in R is false, right? Well, I'm done. Because if AA in R is false to begin with, then I don't even have to bother to look at the other side of the conjunction, because it doesn't matter what the other one is. It's going to be, the entire conjunction is going to be false. But if the conjunction is false, then the implication is going to be true. So that means, if I were to use column E, okay. So AA in R is false, and as a result, the expression is going to be true. So column E is indicating the value of the entire expression. So let's pick another one. I think it was Eric. Yeah, go ahead, Aaron.
Why is AA false?
Because we are working with the example of just having A, B, and AC. I think this is where we are. This is the example that we are working on. Why is it transitive? So AA is definitely not here, right? So AA is in R is false. But if the conjunction is false, then the implication is true. Is that okay? Does it work?
Yeah.
Okay. So since Eric was the one who asked the question, so basically what Eric will need to do is to look at this spreadsheet and find one row here, at least one row here, where the expression, okay, let me show you which expression we're talking about, where, not this one, Okay, so Eric will basically have to find a way so that this expression, which is this part here, is going to be false. Can we choose a value of E, a value of F, and a value of G such that the implication is false? That really is the question. And I argue to say that nope, there's no way we can make the implication itself false. The implication is going to be true all the time. Is that okay? Does everybody understand, how to quote unquote positively prove that a relation is indeed transitive? It's tedious, okay? Basically, you just say, let's consider every single way of choosing a value for the variables E, F, and G, but then we also have to make sure that column E is true for every single case in order for the universally quantified statement to be true. So I'll let you guys kind of sit on this a little bit, and then, when there are no questions, we'll go ahead and move on. Or until somebody yawns. Okay, so I'm assuming we are okay with this one. Okay. Okay, all right, cool. So, but Yalis is absolutely correct. Okay, I missed that one. I missed that BB is not in. Let me see, which one is it? So I missed that BB is not in this one. So my original assessment that it was transitive was actually incorrect because BB is not in here. But that really kind of shows you how tricky these things can be. Because you can see that BA is here and then AB is here. So BB should be here if the relation was transitive. But so that means this is not transitive because it's missing BB in it.
Will this be on exam 1 or 2?
This will be in exam 2. Exam 1 is excluding relations. So it is up to, but excluding relations.
Cool.
Yep. Well, I mean, we still end up with the same amount of material in all the exams. It's just a matter of, schedule, when we schedule that. Because you don't have a homework yet on relations, so I don't feel comfortable putting it in the exam. All right. So are we good so far with being a relation being transitive? Okay. All right.
Yeah.
Okay, cool. So now we move on to antisymmetric. So antisymmetric as a word itself is already confusing because antisymmetric does not mean it is not symmetric, okay? So antisymmetry has its own very kind of strange definition. So when you look at the definition, it basically says no matter how we choose a value for variable E and variable F, okay, they both have to be in X, okay? But it doesn't matter how we choose as long as they are elements in X. And once again, we have an implication, but this time we are basically saying if EF is in R and FE is also in R, then E and F should be the same thing. That is antisymmetry, okay? So if you have a browser on the side, you want to stay on this definition, and then we'll go ahead and look at some examples of whether a relation is antisymmetric or not. So these are examples of antisymmetry. Symmetry, there we go. All right, so same definition of X, okay, just A, B, and C. And once again, we look at R being an empty relation first. So now we ask, is it antisymmetric or not? What do you guys think? Look at the definition again, okay? So I can switch back.
I think it is.
Yep, you're correct. Okay, it is indeed antisymmetric. Why? Now, every time you see an implication, then you just have to ask, okay, one of the questions you can ask is there even a way to make the left-hand side of the implication true? Because if there's no way to make the left-hand side of an implication true, then the implication is always going to be true. Okay, because if the left-hand side of the implication is false, then the implication is true. So in this case, we can see that, well, we got element of, So we know the we know the left-hand side has got to be false when R is empty because there's nothing in R. None of the blah, blah, blah in R is going to be true. So if the left-hand side of the implication is guaranteed to be false, then it doesn't even matter what is on the right-hand side because the whole thing has got to be true, okay? The implication has got to be true. So that's why with an empty relation, it is guaranteed to be anti-symmetric. Okay. So now let's move on to another one. Okay, so let's move on to oh, okay, this one is good. Okay, I'm just reusing this one, and this time I'll remember to cut off the portion that I need to cut off. So now we look at this one and we ask, is this one anti-symmetric?
I think it is not because we have A, B, and BA, but A is not equal to B.
Exactly. Okay. Well, wait, hold on a second here.
I mean, the left-hand side is true.
Okay, so
but
okay.
The right-hand side of implication is not true.
Okay, so tell me what you want to choose as E.
I choose just A and B, A, B, and BA for the left-hand side.
Okay, so you
on
basically
the right-hand side they are not equal.
Okay,
it means yes.
Okay, so Yalets, the way you mention it, basically you have chosen that E equals to A and F equals to B because that's the only time when you can say, you know, this is AB and this is BA, right?
Right.
Okay, so let's check it out. Okay, so this is how we choose. Okay, this is how we choose, and let's see what is the result of this. Okay, let's see what it makes. What is the value of the expression that we're interested? So the value of the expression or the expression itself now becomes okay. AB is in R and BA is in R, and then this entire conjunction implies, okay, right arrow, A equals A. Okay, so now we want to look at this expression here and see if it is true, this portion here. Okay, so now we say AB is in R, is that by itself true? Just this portion here. It is true because AB is clearly here. What about BA? Is BA in R? BA in R is also true. So now we say the entire left-hand side is true. The entire left-hand side of the implication is true. So now we look at the right-hand side. But the right-hand side is comparing A to A. A equals A is true because it is the same value. It is the same element. So that means we have not found a case to make the quantified expression, which is this one here, false. Is that okay, Yales? You know, does this explain, you know, why that particular relation cannot be proven to be not antisymmetric yet?
You mean you prove that it is not antisymmetry?
We have not proven it is not antisymmetric.
But in the left-hand side, left-hand side of implication is always true, right? Because we have A, B, and BA. It is true.
Oh, okay, right, okay.
But on the left hand,
yep, you're right.
Right hand side is
okay, you're right.
false.
Okay, because okay, let me change this here because we're comparing E to F, so we're comparing A to B, so that is indeed false. So it is not antisymmetric.
Yes.
Okay, very good. Sorry about that. That was my fault.
Okay.
Missed that. So that means this is not antisymmetric. There we go. Very good. Let's see whether okay. So let's look at another example. Which one should I use? Oh, okay, I know which one. Okay, so I'll go back a little bit earlier to AAAB. This one, okay. As I scroll on my editor, it scrolls the browser as well, so that's why it kind of things move a little bit. All right, so let's check this out. Okay, is this one anti-symmetric?
I think it is.
Mm-hmm. And how do we know this is
Because
anti-symmetric?
the left hand side is always false.
Always false. Exactly. So the left hand side being this side here is always false. Because if you look at the left hand side, it looks like we are asking for symmetry, right? Or it has some relationship with symmetry. It's not exactly symmetry itself, but it is sort of symmetry. So we can see that EF, we can indeed make this true, by the way, Yalats. If you pick E to be A and F to be A, then EF in R and FE in R would be both true. But in that case, because E and F are the same, the implication is also true at the same time.
That's right.
Yep. And then Omar typed something here. Technically, it is not always false. Yep, exactly. So Omar just repeated. It's the same point that I just made. I think he made that point as I spoke. All right. So that means, in this example, this particular relation is indeed anti-symmetric. So once again, the trick of evaluating these qualities is whether you can make the left-hand side true but the right-hand side false. That is the only way to make an implication false, which is also the only way to make the universally quantified expression false. So that's the trick of looking at these things. Do we have any questions before we move on? If you guys have a particular example that you want me to look into to evaluate all of these properties, go ahead and type that example in the text channel, and then I'll go ahead and talk about it. I'll give you guys maybe like 2 minutes, to think of an example. If nobody wants to talk about an example, that's okay. But we will go ahead and I'll give you guys some time to come up with an example. So until 11:30. So I'm gonna give you guys a little bit of time. You can assume that we have X being ABC, and then you just go ahead and give me a particular R, and it will go through all the 5 properties to see which one is true and which one is false. All right, time is up. And nobody wanted me to go through a particular example. All right. Well, in that case, let me just ask you, how many different relations can I possibly generate when X has the elements A, B, and C? So let me type that question in the on the whiteboard, because I think that's going to be an interesting thing for you guys to think about. I will give you the answer maybe a little bit later, but I just want to give you something to think about, when you have time. Okay, so given that X is A, B, C, how many different relations can be generated? Okay, so that's a question. Okay, I want you guys to kind of think about it. Because we have looked at a few examples, right? All of these are examples of a possible relation that is defined over the set ABC. But I want you to come up with a total number of how many relations can I possibly generate when the set has A, B, and C in it. Okay, so this is a question where I will answer next Thursday, because next Tuesday is our exam 1 day. Okay, so let's move on in the module, okay, because until we get to the end of the module or close to the end of the module, I cannot tell you what the password is for row taking, because it has to do with these concepts. So section 6 is to define what is partial ordering. So partial ordering is actually quite easy to define. It is the conjunction of reflexive, symmetric, and transitive. So if a particular relation is reflexive and antisymmetric and transitive over a particular set, then it is known to be a partially ordered relation. Okay. All right. So given that that is the case, okay, let's go back to our example. So you might want to stay on this particular page, if you have a separate browser, and then we go back to our example here. So we'll say this is about partial ordering, okay? And in partial ordering, let's just say that we have X again, just having A, B, and C as elements in it. So now I want to ask, what is the smallest relation so that it is partially ordered? Now this is not partially ordered because we know the empty relation is not even reflexive. So my question is, what do we need in here, okay, as elements of this particular relation so that this R is partially ordered? But I want the smallest possible relation that is partially ordered. All right, so think about the three requirements, right? One is being reflexive, one is being, let me check again. One is antisymmetric and one is transitive. Okay, so now you have to ask, what is the smallest one that can do this? Now we know the empty set or an empty relation cannot do it because an empty relation is not reflexive. So that means we will need at the minimum AA, BB, and CC to be in the relation. So now we have to look at the other two properties that are also needed in order for a relation to be partially ordered. So one is antisymmetry, okay? So now you look at this particular R here, and then you ask, is that antisymmetric? So what do you think? Do you think it is antisymmetric or not? I'm just putting a question mark here because we're not yet confirming, we are now evaluating.
Yes, I think it is, Professor.
Yep, so it is indeed antisymmetric, because in order for something not to be antisymmetric, you need to select E and F so that they are different, and yet EF and FE are both found in the relation. But in this particular relation, we can see that there's no two tuple that has the first and the second values being different. So there's no way to make the left-hand side of the requirement of being antisymmetric to be true when E and F are different. When E and F are the same, sure, I mean, they can both be A, they can both be B, and they can both be C. But in that case, A equals to A is also true, B equals to B is also true, C equals to C is also true. So antisymmetry is true for sure in this particular R. So then the next question is it transitive? Is this particular R transitive? Remember, to make transitive false, you need to find a bridge element, and then you also need whatever is bridging to be not found in the relation. So in this case, you can say that A is a bridging element because you can now say, what if I make E, F, and G all A? Well, that will make the left-hand side true, right? Because AA is in R is true, AA is in R is also true. But what about the other side of the implication, where E equals to A and G equals to A, right? Then you say, oh, so that means AA is R in R is also true. So that means, okay, yes, we can certainly make the left-hand side of transitive true, in the implication. But if we make the left-hand side true, then we automatically make the right-hand side true based on how we construct this particular relation R. So it is indeed also transitive. So in this case, this is actually the smallest relation that we can define for over X, which only has A, B, and C as elements. It is indeed partially ordered. Okay. Do we have any questions about partial ordering in this case? Okay. Not seeing any questions. I'm looking at the time.
I just want to let you know that I know the answer about the question, but I'm not going to tell that for now.
Okay. Okay.
All right.
All right. So let's move on to the next one. Now, okay, this is where the this is where the key of today's rotating word comes in handy. Okay, so partially ordering is interesting because it means that you have some kind of ordering, but not complete. Okay, so I'll give you I'll present the commercial. This is actually borrowed from a beer commercial. Okay, so we are now looking at smooth versus rich. Okay, and I'm gonna play a video here. Okay, it is really funny. Okay, but it's sort of related to what we are talking about. So let me go ahead and play the video here, and you should be able to hear it as well because everything that is played from my computer should also be presented to. Oh, this is a good question. It may not be. Okay, this is what I'll do. I will put this link into Discord, so this way you guys can watch it too on your own. Because when I play over here, you may not hear the sound, at least not on Discord. If you're watching this on YouTube, you will hear that. Because Discord is not going through the audio of OBS. Okay, I'm just gonna go play it. It's kind of funny.
I'm going downtown. Can I give you a lift?
Sure, thanks.
Smooth. But not rich.
Hi. Can I give you a lift?
Rich.
Sure, thanks.
But not smooth. Michelob Amber Bog. Rich and smooth.
All right.
It was funny.
It was very funny, right? I mean, and we can see a modern day version of this, where somebody pulls up with a Tesla X, Model X, which also has the same kind of door. Sorry.
I think you're looking for the Roadster, Professor Tack.
The Roadster is a little bit low. It's hard to get into. Anyway, Okay, so in these kind of commercials, it is implied that we have some kind of ordering, right? So this is the text version of this. I think it's better to look at this in a spreadsheet format. Okay, so we'll go ahead and use a spreadsheet to look at this. So we have smooth, and then we have rich, okay, and then we have some kind of ordering. So when you look at smooth and rich, then there are 4 ways to arrange things, right? Because you can say, not smooth and not rich. Then you have smooth and not rich. Then you have not smooth but rich. And then you have smooth and rich. So there are 4 ways of arranging these things. So now we look at each combination, and then we want to see how they order, okay? So let's just call this, I just need a label here, okay? This is situation A, B, C, and D, okay? So now we want to evaluate how they relate to each other. In other words, now we are looking at X being A, B, C, D, and A is representing the condition of not smooth and not rich. B is representing the condition of smooth but not rich, and so on, okay? So now we want to define a relation, okay? We want to define some kind of a relation here to basically indicate at least as attractive as, okay? So let me just make this really clear. So R is at least as, no, that is not what I want. Let me go back to my notes. Sorry about that. Okay, I use the abbreviation of ALADA, and ALADA means at least as desirable as. Okay, so that is exactly what I want. So at least as desirable as, okay? There we go. So now, if R is trying to express at least as desirable as, what is it going to look like? So let me put in the items that are really obvious first, okay? AA, BB, CC, and DD. Okay, the reason why these 4 elements are going to be in R is because not smooth and not rich is at least as desirable as, guess what? Not smooth and not rich. So by defining R as at least as blah 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 as, we have just guaranteed that it is reflexive. Does that make sense? Okay, I'll give you a much more graphic, example. I don't do this, but let's just say that I do, okay? Let's just say that I look into the mirror every single morning, okay? And I say, yeah, I think I'm at least as attractive as that person on the other side of the mirror. Is that true?
Yes.
Unless it's a funny mirror. or a mirror that is not exactly a mirror. But assuming the mirror is a true mirror, okay, then that statement is true. So that's basically what reflexive is, okay? So I think this is one easy way to remember what is reflexive, is you basically look in the mirror. Okay, but we have more items than just these 4, right? Because, we also can say anything that has more T's would be more desirable. Okay, now I know this is not what most of you have as your value, but we are just using the beer example, the beer commercial as an example. Okay, so this is not an implication of your value. This is just an implication of the value used or assumed by the beer commercial. But it is really funny. Okay, so we can now say that D, C is going to be in here, okay? Because smooth and rich is at least as desirable as C, which is not smooth but rich, because that is certainly implied in the commercial, because the beer is better than any one of those 2 guys, right? So that means being smooth and rich is definitely at least as desirable as not smooth but rich. But we can now also say DB, okay? because the beer, which is both smooth and rich, is also at least as desirable as B, which is representing smooth but not rich. Okay, the guy who was driving an old Chevy with the door, falling off. Okay, so we can also now say DA, okay, which is kind of implied, okay, because the beer is better than people who are neither rich nor smooth. That was never really shown in the commercial, but it was kind of implied. Okay, what else is it implying? Okay, so now we say, what about C? Now, C is representing not smooth but rich, okay? And it already relates to itself, but it also relates to A, because not smooth but rich is also at least as desirable as not smooth and not rich, okay? And then we also have BA, which is about the same reasoning, because now we have smooth but not rich being at least as desirable as not smooth and not rich. So that is the R that is implied by the beer commercial. It is a partial ordering. Now, why is this a partial ordering and why is it not important? I'll get to that point, but the first thing is I need to let you know what is the passcode of today's road taking. It is the name of the beer, all in lowercase as one word. So let me go back to the beer commercial. And then we play that. I think it is. I'll type it. Oh, okay. Thank you, Aaron. There we go. Not rock. I think it's Amber Bock. B-O-C-K. I could be wrong.
I'm going downtown. Can I give you a lift? Sure.
And smooth.
There we go. Okay, let me.
Rich and smooth.
One more time.
Michelob Amber Bock.
Yeah, Amber Bock. With B-O, that's it. Okay, so Aaron has it typed correctly. AMBERBOCK is the passcode of today's road taking. Yep, I already knew where I would be at the end of today's lecture, so I chose that one at the beginning of the class. Cool. Okay, I got a PM coming in. Okay, that's good. No problem. All right. So now getting to the point that is very important. Okay, why is go ahead.
Right. I spelled that right. Amber Rock.
Amber Bock. AMBERBOCK. Amber Bock. Okay, let me pull this into view. There we go. So it's AMBERBOCK. Amber Bock. All right. Cool. Okay, so the important part here, okay, let me go back to the spreadsheet because this is why it is called partial ordering, okay? So partial ordering is not total ordering, which means you cannot just pick A, B, C, D and always be able to say this one relates to this one in this particular way. So in this case, B and C are not related. So B, C is not in R. And on top of that, CB is also not in R. In other words, the two guys in the commercial, the one who's driving a Chevy and the one who's driving a sports car, there's no ordering between those two. Okay, we cannot tell whether smooth but not rich is at least as desirable as smooth but not rich. We cannot order between the B and the C. Is that okay? And that's why it is only partial ordering and not total ordering. Because in total ordering, if a relation is a total ordering, then you can pick any two things from the set, okay, that the relation is defined over, and I can tell you how those two relate, okay? I will give you one really, really simple example, okay? So think about x as the set of all integers, okay? So we are now looking at -5, 2, 0, 100, -2000, and so on, okay? And the relation is less than or equal to. So when you think about that, okay, That is a total ordering, because you can always pick 2 integers out of the set of integers, and I can tell you whether they relate by less than or equal to. Does that make sense? But in this particular case, when we are looking at the beer commercial, it was never implied or explicitly stated whether rich but not smooth but not rich is at least as desirable as smooth but not rich or not, or the other way around. So that was never implied. So we don't have an ordering. These two, B and C, do not relate to each other in this particular relation. And we are actually out of time, but it is also important for me to kind of just finish this little bit, because if I don't do it now, then we'll be doing it like next Thursday, where we'll all be forgetting the context of this discussion. So the important part of whether something is partially ordered or totally ordered has to do with sorting. Okay, now since CISP440 is a co-requisite of this class, so I'm assuming most of you know what sorting is about. When you have a set of elements that is only partially ordered, then you cannot always sort the items. In other words, in this case, I do not know the actual order between the B and the C, because they do not relate to each other. I cannot tell which one should go first. So that is important, because when we look at a lot of applications, especially every time that we want to do any type of ranking, we need total ordering. Partial ordering is not enough when we want to rank things. Now, what kind of ranking are we talking about? Well, in our society, we rank things all the time, don't we? Okay, we have, if you play video games, it would not be unusual that they would say, who is the gamer of the week? Okay, if you watch Hollywood, okay, Hollywood always have some kind of ranking. Okay, who's the best? Okay, who makes the most money, and so on and so forth. So you would say, well, but money, how much money a person has, is totally ordered, because it really is just a number, right? And numbers are totally ordered if you just look at less than or equal to, or greater than or equal to. But when you look at how you choose quote-unquote gamer of the week, then you have a few parameters. You got parameters like how much money did they spend on the game, okay? Because certainly game developers like in-game purchases, okay? Because that's money. But you also can look into win-lose ratio. You can also look into how a particular gamer is evaluated by peers, okay? Especially in e-sport type of game, where whether a gamer can work well with other gamers, whether they get a lot of thumbs up from their teammates or not, that can also be a factor. So the way we combine these numbers into comparison, into ordering, sometimes if we are not careful, we may end up using a function that is not totally ordered. Because when you're combining several numbers and you only want to evaluate whether a particular player is at least as eligible as gamer of the week as another one and as another gamer, we can accidentally define a relation that is not totally ordered. And that means we cannot sort, and when we cannot sort, then we cannot always rank. In other words, we might end up with a whole bunch of people where they are better than many other people, but within this group of people, there's no ordering that we can actually apply. And yet they are not the same. Okay, so we are not talking about the same person. We're talking about multiple people where we cannot find ranking amongst them. And that is a problem when you have to find the gamer of the week, because you only need one person, or you need some kind of metric where you can say these people all meet the same requirement. So that is why partially ordered versus totally ordered is important in computer science, because it has to do with ranking, sorting, and picking quote unquote the first one of the entire list. So that's it. Okay, that basically concludes our discussion of relations, at least for the time being. And don't forget, next Tuesday is our exam 1, and I want you guys to let me know what time slots you cannot make it by using a checkbox in the form, latest by sometime tomorrow. In other words, on Saturday, I will go through that, all the data that I have collected, and then I will start to assign people to time slots.
Professor,
yeah, go ahead.
What exam? I'm still not clear about this exam. How would
how it's going to be conducted?
Yeah.
Okay,
I don't.
I'll give you guys a description. So what will happen is I have a program to generate questions. So the questions will be basically Google Docs, but it is going to be specific to each person. So each exam question is going to have a student ID associated with it. Mm-hmm. And then what will happen is, based on your availability that you submit using the form, okay, now remember, you check a box of the time that you cannot make it. Okay.
Yes,
so
I
remember
did.
that.
Yes.
Okay. So based on that information, I would know what time slot you are available, and then based on that, I will have a program to assign people to different time slots. So within the time slot that you are assigned to, at the beginning of that time slot, I will share a Google Doc with you, and that's only shared with you and no one else. At the end of the time slot, my script will also unshare the same document. So you basically have that entire time slot to answer the question, and you just write your answer in the document itself.
So you're going to send us some kind of email, or you're going to put it in Canvas?
It is not in Canvas. Basically, it is it's a Google Doc being shared with you, which means you usually get a notification using the apps.losreals.edu Gmail.
Okay. It means I'm going to receive it automatically?
Yes. So you will receive a notification through the apps.losreals.edu Gmail that a document has been shared with you from me. And as soon as you receive that document, you can go in and start your test. So that usually happens a few minutes before the time slot that you're assigned to. Go ahead.
So is it any time restriction? I mean, you said we're going to have an hour or what?
It's going to be 80 minutes. It's the same amount of time as one lecture.
Okay, thank you.
Yep. So there's no emailing, okay? Aaron, there's no need to email me back the document because it is shared with you at the beginning and then it is unshared automatically. And because I only share one document per student, I know exactly whose test it is.
So could you please just send us what time you should sign for us?
Yes. Yep. I won't be able to do it until Saturday because I want to collect feedback from people on Friday.
Great. Thank you.
Yeah, sure. And then Kevin says announcements. Yep, I will have announcements. I will have announcements about the process, but each person will get an individual email about the time slot. What time slot they are assigned to. Oh, okay, I see. Yes, so the availability survey is out. Check your apps.losreals.edu email because the announcement should be forwarded to your apps.losreals.edu Gmail. But if not, you can always go to the announcement of the class and the link to the survey is there. Or you can just click on the one that Aaron just posted. I think that's the announcement itself. All right, so any other questions?
Tack, when lecture is over, you might want to fix your camera. It's not getting the entire mirror.
Oh, that's fine because that's actually intentional.
All right.
It's intentional. Well, in in photography, we call this, using part of the setting, part of the environment as the frame. But in this case, it's basically me not wanting my face to fill up the entire frame, because I don't like to look at myself, even though I usually don't look at the OBS screen. I just don't want my face to fill up the entire frame. But that just it looks really awkward when I'm in Zoom meetings with other people, because in a Zoom meeting with other people, the proportion of my face to the entire frame right now is about average. Okay, but okay, I can show you guys what happens when I zoom in. So when I zoom in, it looks like this, right? So now in a class setting like this, it doesn't look too awkward because you don't have any comparison. It's not like you have a whole bunch of other people, with their pictures in tiles. But in a meeting where you have 20 something other people, and the proportion of their face is a lot smaller compared to mine, it really stands out. So that's why I kind of zoom out. But when I zoom out, you see the frame, because the thing that I use, has doesn't let me, it just doesn't, the mirror is not big enough. So the frame of the mirror, shows up in the video. So that's why, Aaron. All right.
Thank you so much. Have a nice day.
You too. You guys go get your lunch and have a nice weekend. Good studying. Yep. And make sure that you have enough energy, sleep well before the exam. All right. Cool.
Thank you.
Thank you. And this is the beginning of my office hour. So, I'm just going to hang around on Discord and answer questions, but not through the voice channel. All right. You guys have a nice weekend. I'll see you guys on Tuesday sometime.
Goodbye, Tuck.
All right. Goodbye.